of the elements matter. If you change the order, then the vector changes as well. So by default, we'll assume every time we say we have a d-dimensional vector, we arrange the elements in this vector vertically. So when you write it down, it usually looks like this. So this is called column vector. By default, we assume any vector is a column is a column vector. But of course, in some kind of situations, we can arrange elements horizontally. So we can represent a d-dimensional vector in this way. So this is referred to as a row vector. And this is about the definition of vector. And then what about matrices? So as the name suggests, matrices are arrays of elements. So when we say okay, we have an m by n matrix, it means that it has m rows and n columns. So it has mn elements in total. So we can, if we write down the full matrix, we can enumerate its element row by row. So the first element, the element in the first row is A11, A12 until A1n, right? Because it has n rows. The second row is A21, A22, A2n, and we can enumerate in this way, and finally we end up with mth row. It's AM1, AM2, AMn. So each element in matrix A can be indexed by two integers I and j, right? I indicates the row where this element stays, and j indicates the column. So aij indicates the elements which stays in ith row and j's column in matrix A. So these are the basic definitions, and actually linear algebra are kind of topic about how we manipulate or how we make operations on those vectors and matrices. So let us first look at the first basic operation. It's called transpose. So what does transpose mean? So if I do the transpose, so let me write it clearly. So transpose operation, denoted by like T. If you put a superscript on A, we usually mean we are transpose A, right? So what's the result matrix for the transpose of A? Anyone recall? Yeah, n by m matrix, right? The original matrix is of size n by n, and then transpose A will end up with n by m matrix. Then how are the elements in A transpose are arranged?
A1
Yeah. So in its transpose, we just put the first row in our original matrix in the first row in the transpose. Right? So the first column in A transpose would be A11 because it corresponds to this row, right? And A12, and A1n. And the second column in A transpose would be the second row of the A, right? So it is A21, A22, A2n. And then we can enumerate each column in A transpose. And finally we end up with the last column, which corresponds to the last row in A, which is AM1, AM2, AM. So this is A transpose. And it's easy to say that A transpose is of size n by m, because you have like n rows and m columns right now. So give you a simple example. Suppose A is a 3 by 2 matrix, right? 1, 2, 3, 4, 5, 6. So what is A transpose?
2 by 3.
Yeah, first we need to know its size, right? It's a 2 by 3. And now we just write down its elements in A transpose column by column, right? So first column corresponds to the first row of A, which is 1, 2. And second column corresponds to the second row in A, which is 3, 4. And accordingly, third column is 5, 6. So this is A transpose. And now let us try to apply the transpose over vectors. So if I apply transpose operation on a column vector, then what do we end up with?
Row vector.
Yeah, the row vector here, right? So a column vector is essentially a d by 1 matrix, right? So if we do the transpose, it becomes a 1 by d matrix. Right? So it is a row vector. And similarly, if we apply the transpose over a row vector, what do we get?
Column vector.
Yeah, column vector, because this is a 1 by d, and you transpose d by 1, you switch the number of columns and rows. So now, let us talk about the mathematical operations among several or multiple vectors and matrices. So the first basic operation is called addition. I assume all of you guys have taken this linear algebra class in your first year or second year, so our pace will be a little faster. Yeah, some of you may feel quite boring, so that's just a relatively quick review. So we can add two vectors or two matrices. So if we add two vectors, what do we need to require?
It's the same size.
Yeah, it must have the same dimension, right? You cannot add a three-dimensional vector by a two-dimensional vector. So they must have the same dimensions. Then what's the result? What's the result of V plus W? Suppose they are both d-dimensional vectors.
Prediction of each element corresponds.
Yeah, it will result another d-dimensional vector, and each element is the corresponding addition of the two elements in V and W. So it will end up with V1 plus W1, V2 plus W2, and VD plus WD. And here we assume by default V and W are both column vectors. Of course, you can add two row vectors, but actually you cannot add a column vector by a row vector because their size or their shape is not consistent. And similarly, we can add two matrices, A plus B. And when we add two matrices, we must ensure that the size of A and B are exactly the same. So the size of A is n by n, then the size of B must be n by n, right? So the result matrix, suppose C, is also n by n. And each element in C, like let us denoted by Cij, right, is equal to what?
Aij plus Bij.
Yeah, is equal to Aij plus Bij. So it's a very straightforward extension from the scalar addition, scalar additions. So this is an addition. And the second operation is called multiplication. This one is a bit different from the commonly used scalar multiplication. So we first consider the simplest case. That is, we multiply a matrix, a vector, with a scalar. So we can multiply a scalar alpha by a vector b. Then what's the result vector? You just multiply alpha into each element in V, right? So you will end up with another d-dimensional vector. So it is C alpha C1, alpha C2, alpha C D. Suppose, oh sorry, it's not C. It's V. V1, V2, and VD. So you end up with another d-dimensional vector. Assume V is d-dimensional. And similarly, we can multiply a scalar alpha with a matrix A. So it will result in another n by n matrix. So each element will be the alpha multiplied with the corresponding element in A. So basically, in this new matrix, each element at ij is alpha times aij. So it's pretty straightforward. But then let us look at a more complex case. So what if we want to multiply two matrices? A multiply B. A multiplies with B. Then what kind of requirement do we need to perform the multiplication? An idea?
Should match the row.
Yeah. This is a very important constraint. This is regarding the definition of matrix multiplication, so it must be very familiar with. So suppose if we want to multiply two matrices A and B, we must ensure that the number of columns in the first matrix is exactly the same as the number of rows in the second matrix. With that being said, if the matrix A is of size n by n, then the matrix B must have the n rows, right? So matrix B must have n rows to be consistent with number of columns in A. But of course, matrix B can have an arbitrary number of columns. So this is a basic requirement. And then how can we compute this multiplication? So first we need to know that what's the result of this multiplication. What's the result of this multiplication?
M by D matrix.
Yeah, it is another matrix. And we need to know that the size of the result matrix, which is M by D, namely the number of the product has the same number of rows in the first matrix, and the number of product has the same number of columns in the second matrix. So actually, you remove the effect of the number in the middle, which corresponds to the number of columns in the first matrix and number of rows in the second matrix. So this is some kind of basic rule. You must every time we talk about the matrix multiplication, this is something that must immediately come into our mind. It's very, very basic. So now let us review how can we compute this multiplication. Namely, how can we compute each element in this product. So how can we compute a specific element, Cij, in the matrix C? Namely, the element at ith row in C and jth row in jth column in C. So we know that the row I must be between 1 and n, j must be between 1 and d, right? Because I index the row and j indexes the column, right? And how can we compute this element in terms of A and B?
A of I times B of J, the row times the column.
Yeah. So actually, to compute Cij, we'll need to look at the ith row in A and then jth column in B. So let us first write down a formula, and then we look at the look at in terms of the range of elements. So basically, we multiply each element in ith row of A with the corresponding element in jth row, jth column in B. So we multiply AI1, the first element in ith row of A, right, with the first element in jth row or jth column in B, which is B1J. And then second multiplication between their second elements, which is AI2 times B2J. B2J index the second element in jth column in B, right? And we do it. We will continue to do it until we multiply with the last element in ith row for A and the jth column in B. So the last element is AIN, and the last element in jth column in B is BNG. So now we can say why we must require the number of the columns, that is the length of each row in A, must be exactly the same as the length of each column in B. Because we need to perform this computation, their length must be consistent. So a succinct representation would be just use this sigma notation, right? So we start from k from 1 to n is actually here. And in this summation, it is a product between aik and bkj, indicating the kth element in ith row in A and the kth element in jth column in B. So this is a rule to compute each element in the product matrix. And now we can take a look. In terms of matrix arrangement, element arrangement matrix. So this is A, right? And let me write down B. B is another matrix. So we can look at the ith row in A. So let me write down here. AN1, AI2, AIN, right? It has n elements. And then we can look at the jth column in B, so which is B1J, B2J, BNJ. So this is the jth column, and this is ith row. So to compute, so for C is the result product. This is CIG, which corresponds to ith row in C and jth column in C, right? To calculate this single element, CIG, what do we need? We need to look at ith row in A and jth column in B, right? And the calculation is that we multiply AI1 with B1G, right? The first element, their element-wise multiplication, add the multiplication between the second element in ith row and second element in jth column. And we do this continuously until we reach the last element in ith row of A, right? This AIN multiplied with the last element in jth column in B, with this, and add them together. We'll end up with CIG. And we can repeat this computation and to enumerate every element in this result product matrix. So this is a very basic operation on matrices and vectors, and you should be very, very familiar with that, because in the future, if you want to do some machine learning or data science algorithm development, you want to develop models and algorithm, you will so nearly every step of your derivation, you have to consider this kind of operations. So some properties regarding the matrix multiplication. So first, matrix multiplication is associative. So what does associative mean? So here is an example. Suppose we have 3 matrices, right? So when we first multiply A with B, and then multiply this AB with C, this result is exactly the same as we first multiply B and C, and then multiply A with the production between B and C. So this is called associative, meaning that you can combine in this chain of the production. You can combine any of those elements, any of those matrices, and perform the multiplication together, and then do the multiplication later. It doesn't matter. So this is consistent with the scalar multiplication. Scalar multiplication associative is very natural. And second, matrix multiplication is distributive. So what does distributive mean? It means that if we multiply a matrix A with a summation of 2 matrices, so B and C, it is equal to, we first do the multiplication and then do the summation. So it's equal to AB plus AC. So of course, this also applies to the summation of more than 2 matrices. You can have B plus C plus D, and you end up with AB plus AC plus AD, and etc. So this is also consistent with the distributive law in scalar multiplication. But third one, you should be very careful. That is matrix multiplication is usually not commutative. So to be most rigorously, I should add usually. There are some special cases they are commutative. But usually, matrix multiplication is not commutative, meaning that the order 2 matrices are multiplied matters much. So usually means that the product between A and B usually is not the product between B and A. To simplify, to simply verify that, we can consider 2 matrices A and B, and let us check what's the size after multiplying A with B, and what's the size after we multiply B with A. So if A can multiply B, and B can multiply A, then what's the size? What are the sizes of A and B? Suppose you know A is n by n. So if we can multiply A with B, and at the same time we can also multiply B with A, then what's the size of B?
N by n.
Yeah, n by n. You can check with that. So first, if we want to multiply A with B, then the number of columns in A must be consistent with the number of rows of B, right? So meaning that B must have n rows, right? And if you want to multiply B with A, then similarly, the number of columns in B must be consistent with the number of rows in A, meaning that m, the number of columns in B must be m. So you can verify that. So now we can look at. So what's the size of production between A and B. When you multiply A with B, what's the size of result product?
M by N.
M by N, right? Then what's the size of the product between B and A? It's N by N. So if you take different values for M and N, then the result two products actually have different sizes. So say M is 2 and N equals to 3. Then you multiply A with B, you end up with 2 by 2 matrices. 2 by 2 matrix, and you multiply B with A, you end up with a 3 by 3 matrix. It's not possible to be exactly the same between two matrices. So these are the basic definition of multiplication. So and actually, we can also define the multiplication between vectors. They are essentially special instances of matrix multiplication. So we may talk about two types of production or multiplications between vectors. So the first one is called inner product. So if we want to do the inner product between two vectors v and w, what do we require? An idea?
Be the same size, right?
Yeah, they must have the same dimensions. Same dimensions. Suppose they have they are both d-dimensional. Then the inner product, which is usually denoted as like this, it is a scalar. So first keep in mind, it is a scalar. And the computation is simply the element-wise production between each element in V and each element in W, and then add them together. So it is V1 W1 plus V2 W2 plus VD W2. So this is the definition for inner product. So inner product, the requirement is that the two vectors must have the same dimension. And second, that it returns a scalar. So now let us consider how can we represent the inner product in terms of matrix multiplication. As we just mentioned, it is a special case of matrix multiplication. So how can we represent inner product as matrix multiplication? So by default, we know two d-dimensional vectors v and w are two column vectors. Okay? So this is v1, v2 to vd. So this is v. And similarly, this is w, w1, w2, wd. So column vectors mean that we both are d by 1 matrices. And then this inner product can be represented by what?
So V times W transpose, sorry.
Yeah, you're very close, but it's a little incorrect. So actually, remember, this is a scalar, right?
V transpose.
Yes, V transpose. So this actually equals to V transpose W. Why? So if you do V transpose, then what's the shape of V transpose? 1 by D, right? So 1 by D, horizontal shape. It's 1 by D matrix. And then you multiply W, which is D by 1 matrix. Then what's the result? It's 1 by 1 matrix. What is 1 by 1 matrix? Yeah, it is a scalar. 1 by 1 matrix is a scalar. Then you can check, following the matrix multiplication rule we just reviewed, it is exactly this. So similarly, we can also do the transpose of W and then multiply with V. They are exactly the same. So this is called an inner product. And second common with production between vectors is called autoproduct. So in autoproduct, first we don't require the two vectors V and W to have the same dimensions. So V can be like D dimension, and W could be arbitrary other dimensional, like Q dimension. And the autoproduct, so let me use a circle to represent the autoproduct. Of course, there are other notations. So the autoproduct between V and W is no longer a scalar anymore. Actually, it ends up with a matrix, a D by Q matrix. This is the autoproduct. So before I introduce how we compute this matrix, let me give the definition in terms of the matrix multiplication. So the autoproduct between V and W is actually the product between V and W transpose. So now we can say V is a column vector, means that it is a D by 1 matrix. And W is a Q by 1 matrix. So when you do the transpose, it becomes a 1 by Q matrix. So now, when we multiply a D by 1 matrix with a 1 by Q matrix, the worst size of result matrix will be D by Q, right? And then we can consider to compute this matrix by following this. So for a more clear illustration, so let us just write down. So V is represented by its column form. So D. And when we transpose W, we end up with a row vector. So it is W1, W2, WQ. And then we can apply the matrix multiplication rule by doing the multiplication between these two matrices. So the first element will be V1, W1, and second V2, W2. Oh, no, sorry, it's V1, W2, and V1, WQ. And similarly, second row will be V2, W1, V2, W2, until V2, W2. And you can enumerate. It's just enumerate all possible production between the elements in V and W, and arrange them in this matrix. So it's so the last row would be VD, W1, So this is the definition for autoproduct. And something you should be aware is that if we do the inner product, we do inner product between V and W, it is exactly the same as the inner product between W and V. Right? Because they both return a scalar. And according to the definition, you switch W1, V1. Doesn't matter. But for autoproduct, if you do the autoproduct between V and W, it's usually not equal to you do the autoproduct between W and V. Why? Yeah. You can just check it with the size, right? So V autoproduct with W is D by Q matrix. But if you do the W autoproduct with V, it's actually Q by D matrix. So it's different. So now let us consider to combine the inner product with the scalar product. So how about we first multiply scalar alpha with the vector v, and then do inner product with another vector w. What does this equal to? What does this equal to?
Times the inner product of V and W.
Yeah, this is simply equivalent to we are pulling alpha outside this inner product, and then do the inner product. So this is pretty easy to check because you can use the definition here, right? So alpha v, the inner product between alpha v and w would be alpha v1 w1 plus alpha v2 w2 plus blah 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 alpha v d w. And now you just extract alpha outside this summation. You end up with this. A second property. So how about I do the inner product between v and the summation of two vectors, say x plus 1. What's the result of this? What's the result of this? So let me first give you the conclusion. It's actually a special case of the distributive law, as we just mentioned. So it is the inner product between v and x plus the inner product between v and y. You can verify it either from the definition here. Now here, w, each element in w will be expressed as like x1 plus y1, x2 plus y2, right? Then you can distribute the summation to the multiplication, or you can check using the matrix multiplication. So this is actually a typical instance of distributive law in matrix multiplication. Now combine the two. A commonly used trick is to decompose the inner product between a scalar multiplication of alpha v and summation of two vectors x plus 1. And combine them, we can immediately obtain what? It is equal to you first pull alpha outside this inner product and then apply the distributive law. It's 3x. So this is pretty straightforward and very simple, but actually, as you may review in the advanced topics in linear algebra, like orthogonal space, like linear space, and orthogonal Schmidt decomposition. Those kind of tricks are often used, although it's really easy and obvious. But sometimes those tricks play a very important role, central to simplify a formula and arrive at your conclusions. And similarly, when you derive some models in terms of linear classifiers, because linear classifiers are talking about the inner product between the classification weight vector and your feature vectors. So you want to derive a bunch of properties regarding your linear models. Those tricks are often used. So now let us consider matrix vector multiplication. So we can multiply a matrix A, say m by n, by a vector v. If we can multiply A and V, then what's the requirement for V?
It says n dimensions.
Yeah, V must be an n dimension. So by default, V is a column vector, so V must be n-dimensional, meaning that it is n by 1 matrix. So what's the result of A multiplying with V?
Row.
It's not a row vector. It is another vector.
Yeah.
Because n by n matrix multiplying with n by 1 matrix end up with a n by 1 matrix, right? N by 1 matrix. So let me denote that's why. N by 1 matrix is actually my m-dimensional vector. And then how can we compute it? How can we compute it? We can just follow the matrix, the definition of matrix multiplication. So this A11, this first row, A11, A12 to A1n. Second row, A21, A22 to A2n. And last row, AM1, AM2 to AM. Then you multiply this column vector, which is V1, V2 to Vn. So the result y. Y here. So how can we compute the first element in y? According to the definition, right, we need to look at the first row in A and first column in V, right? V only has one column. So actually you do the element-wise production between elements in A, the first row in A and V. Then we end up with a scalar. And similarly, the second element is the elements product between the second row of A with elements in V and add them together. So if we instead represent each row vector in Y by like A1, A2 to AN. Sorry, it's not in Y, in A. So now A can be represented as stacking M row vectors. So it is A1, A2 to AN. So now, when we multiply matrix A with this vector V, it is essentially to multiply each row vector of A with this column vector V. So there's A1, V, A2, and AM. M elements in Y. And because this is a row vector and this is a column vector, so it ends up with a scalar. So if we write down as a column version of A1, like to be like A1 bar, right? So actually this product is the inner product between A1 bar and the V1. Right? And similarly, this is actually the inner product of A2 bar and A2. V. Because this is a column vector, this is a column vector, and their inner product is actually their transpose, because this is a row vector, and multiply with V. So this is a block matrix view of doing the multiplication. So those are the most important computations or operations over vectors and matrices. And although it sounds manual, but the core principle or the core rule is the definition of matrix multiplication. So whenever you multiply several vectors and multiply matrices with vectors and matrices with matrices, or the hybrid of them, they essentially follow the same computation rule, that is matrix multiplication. And next, we introduce the important concept called norm. Norm. So we can define norm over vectors and matrices. So we start with norm. So what does norm mean? In the context of vectors, you can consider norm as length. Right? We start with the Euclidean norm. Suppose in this two-dimensional space, so a two-dimensional vector is actually represented by U1, U2. Suppose this is a vector U. Right? So we know that the vector also in a two-dimensional space can also represent a point in this two-dimensional space. Right? Suppose this is a point, and its x coordinate corresponds to u1, and y coordinate corresponds to u2. So what's the length of this vector? What's the length of this vector? How can we compute this length of vector? Yeah, you take square sum of u1, u2, and take square root. So the length of u, here I use double vertical lines to represent the length, is actually u1 square plus u2 square, and then take a square root. No problem with this, right? This is u1 and this is u2, and it is perpendicular triangles, right? We calculate this. This is a u1 square plus u2 square. And similarly, if you use a three-dimensional space such that your vector u is u1, u2, and u3, then what's the length of u? You just take the square sum of their x, y, z coordinates and take square root. So this definition actually can be extended to a d-dimensional space, arbitrary dimensional space. So suppose u is a d-dimensional vector, then we define its length. It's the square root of the square summation of each element. So it's u1 square plus u2 square plus u3 square. It's very intuitive concept of the distance, and if you write it down as a succinct form, it is a summation, y from 1 to dimension d and ui squared. This is a special norm for the vector. It's called Euclidean norm or L2 norm. It's called Euclidean norm. And for the Euclidean norm can be generalized to LP norm. So let us define what is LP norm. So basically LP norm, we denote LP norm with this subscript P. It's defined as, we first take absolute value for each element in U. So U1 absolute value, and then 2 C. And plus also the second value, second absolute value, U2 to the P. And add them together until U2 to the P. And then we'll sum them together and take 1 over P. So this is called LP norm. This definition sounds a little weird at the first sight, but it's a very, very common use. So we can say when P equals to 2, it goes back to the Euclidean norm. When P equals to 2, then each absolute value to the P becomes a square. Right? And outside it becomes 1 over 2. 1 over 2 is the square root. So actually, Euclidean norm is L2 norm. But of course, we can use arbitrary P. But P must be no less than 1. There's a very interesting norm called, which is also a special instance of LP norm called infinity norm. That is denoted by U infinity. So it's actually the limit when P approaches infinity, the LP norm of the LP norm of U. And it turns out to be the maximum absolute value, and the maximum absolute value of the elements in U. So infinity norm is the maximum absolute value among all the elements in U. So I will leave the proof of this as your exercise. So to refresh your mind about the definition of limit. There's a very simple proof to show that when you calculate the limit when p approaches infinity, it is exactly the maximum absolute value of the elements. And Euclidean norm and infinity norm are very commonly used. Also, there are also L1 norm. Is also quite common use, like in sparse learning. That is a branch of machine learning research. So we can understand LP norm in another point of view, namely, it is a kind of a distance metric. That is, we can consider two vectors, U and V. We first subtract the two vectors, U minus V, and then take LP norm. And actually represent a kind of distance between U and V. So remember, U and V are 2 points in the d-dimensional space. Right? So actually, between any like abstract points, we can define corresponding metric of their distance. So consider p equals to 2, meaning that we go back to the Euclidean norm. So in this d-dimensional space, we have two vectors U and V actually represent 2 points in the d-dimensional space. Right? So what's U minus V? It's actually a vector, right, starting from V to the U. Right? And then you take L2 norm, namely Euclidean norm, is actually the distance, Euclidean distance between U and V. But of course, you can define all kinds of other distance. The Euclidean distance is the most familiar distance we know in our world, like in the human's world. But in abstractive world, you can define all kinds of distance. Then the interesting question would be, what kind of distance metric do you consider to be valid? So this is something you should be aware. So distance metric. So we can define for any two d-dimensional vectors a distance metric to measure the closeness between them. Then to define such a distance metric, what kind of properties do we need to satisfy? You cannot return an arbitrary number as your distance. Right? Then it must satisfy some properties. So first property is called symmetry. Namely, in your distance metric, DUV must be exactly the same as DU. So meaning that, okay, the distance between you and me is the same as distance between me and you. This is intuitive, right? If they are different, then it's not consistent. And second property is called non-negativity. Namely, the distance metric for any two vectors, U and V, must be no less than 0. And if they are 0, if and only if U is exactly equal to V. This is also intuitive, right? First distance metric cannot be negative, right? So where does the that mean for a negative distance, right? And you and me is like negative 3 miles away. What does it mean? Right? So in the closest, if you and me are closest at the extreme, our distance should be 0. Right? And in this case, we need to ensure that we overlap in the position in this d-dimensional space. So this is also intuitive. And the third one is kind of not easy to come up. It's called a triangle inequality. What does triangle inequality mean? So basically, we consider 3 d-dimensional vectors. So your valid distance metric should guarantee that the distance between u and v must be less than or equal to the distance between u and w plus the distance between w and v. So from geometric point of view, what does it mean? So this is u, this is v, by 2 points. Their distance must be less than the distance, the third point, w, right? The distance between u and w and v. So consider 3 points, right? This forms a triangle. So we know that the length of the edge for any edge in this triangle must be smaller than the summation of the length of the other edges. That's why this is called a triangle inequality. So basically, if you want to travel from u to v, the shortest path is a straight line between u and v, right? Rather than you first travel to another point w, and then from w you travel to v. So this is called triangle inequality. So any distance metric, if it satisfies these 3 properties, this is called valid distance metric. And you can show that LP norm is a valid distance metric. So LP norm is a special distance metric. That's it. So you're not required to prove that why LP norm is satisfy these 3 distance metrics. And here we mention this concept because in machine learning there is a branch called metric learning. Namely that I assume some space, I assume some metric, distance metric, and then how can we learn this metric? But we need to ensure these metrics must satisfy these 3 properties, right? But we actually don't know how can we, what's the parameters that determine the metric. Then can we learn this metric from data? This is a branch of machine learning. So now let us look at the norm for the matrices. So there are quite a few definitions of matrix norms. But what you need to know are 2 common used norms. One is called Frobenius norm. So suppose we have a matrix A, right, n by n. And Frobenius norm of A is denoted by, this is similar to the norm of the vectors, the notation, but we use a subscript f to denote the Frobenius norm. But Frobenius norm is very similar to L2 norm, namely Euclidean norm. That is, you just do the square sum of all the elements in A and then take the square root. So basically, we add the square of each element in A. So A, I, J, squared. And then take square root. That's the Frobenius norm. Very simple. And a way to memorize Frobenius norm is that you can imagine you vectorized the whole matrix A into a long vector, right? And then you calculate the Euclidean norm of that vector. Then you end up with Frobenius law. And second common use norm is called spectral norm. This is not that intuitive. So here is the definition. First, the spectral norm is kind of confusing with the L2 norm for vectors. So remember, if there's a matrix here and you even have a subscript 2 here, then this is not L2 norm. This is spectral norm. And it's far from the L2 norm. So the L2 norm, the spectral norm, is defined as a maximization over this value. And X is a n-dimensional vector which has non-zero norm. So this is the definition of a spectral norm. So it sounds weird, and to me it's weird as well. But all you need to do is that you know this kind of norm definition. And in simple case, you should be able to compute this norm. So basically, spectral norm says that I just want to enumerate. So here we assume A is n by n matrix, right? We just enumerate all possible non-zero n-dimensional vectors. And for each n-dimensional vector x, I compute the value. That is, first multiply A with x. It ends up with another vector, right? Then we compute this Euclidean norm. Then we divide this Euclidean norm with the Euclidean norm of x itself. This is the value, right? And then we enumerate all kinds of such non-zero x, and we end up with all the possible these values, and pick up the maximum as the spectral norm. So this is the definition of spectral norm. This is not very intuitive, but in the optimization procedure, this is very common use, heavily used, because it can be easily converted into a maximization procedure. Maximization is the optimization procedure. So now, based on the norm and based on the norm of the vectors, I want to help you to review a little geometric interpretation about the vectors. So suppose we have two vectors u and v in this d-dimensional space. We can move the two vectors such that one of their star end overlaps. Right? This is u and this is v. Then we know there must be an angle between them. And there is a way to compute the cosine of their angle. How can you compute it?
The distance from U to V. That's it.
Yeah, you can derive that. But let me tell you the answer. So the cosine angle between the two vectors u and v is equal to the inner product between u and v divided by the Euclidean norm of u multiply the Euclidean norm of v. Probably you have already met this formula in your calculus course or even in high school course. So here is just a review, and you can exercise to prove this. And now let us consider: what if sum of the one vector, say v, has the Euclidean norm to be 1? What does it mean? So first, if a vector has a Euclidean norm being 1, we call this v as a unit vector. As the name suggested, because the length is 1. And it's also called direction vector. Why? Because a vector actually has two properties, right? One is direction, the other is length. And now length is standardized, it's 1. Then the only information represented by this vector is this direction. So this is also called direction vector. Then what if we do the inner product between an arbitrary vector u and the unit vector? What does it mean? From geometry point of view, it actually indicates the length of the projection. So we can look at this formula again, right? We can look at this formula again. So now we multiply the denominator with cosine theta. It is the numerator, right? So inner product between u and v will be the norm of u times the norm of v, then multiply the cosine theta, cosine angle, right? So now we know v is unit vector, meaning that this norm is 1. So we can simply erase it. So what does this mean? We can take a look, right? So the norm of u indicates the length of u, right? So it is the length of this. And length of u multiplying with cosine theta. What does it mean? If you draw a line which is perpendicular to v, right, cross the end of u, right? The norm of u, meaning the length of this edge multiplied cosine theta, is actually the length of the projection. So that means if you calculate the inner product between an arbitrary vector u with a unit vector, then this inner product, it is the length of the projection. You project u to this direction. This is also another commonly used geometry interpretation. So in the remaining 5 to 6 minutes, we'll review the last concept today. It's called linear independence. Or dependence. So it's actually discussing the relationship between a set of vectors. So let us define a set of vectors x, right, as key vectors, x1 to x. So each vector belongs to a d-dimensional space. So each vector is a d-dimensional vector. So suppose we have a third vector, the k plus 1 vector z is also d-dimensional. And if we can represent z in terms of x1, x2 to xk, meaning that we can find out k coefficients, alpha 1, alpha 2, alpha k, such that we can represent z to be alpha 1 times x1 plus alpha 2 times x2 plus alpha k times sk. So here alpha 1, alpha 2 to alpha k can be 0. Arbitrary real value you can choose. So as long as you can choose a set of coefficients alpha 1 to alpha k to represent z as a linear combination of the vectors in X, then we call z is a linear dependent on X. This is the definition of linear dependence. Simply, it's just saying, okay, if I can represent some extra vector by a linear combination of a set of existing vectors, then we call it a linear dependent. Then what if we cannot find a set of key vectors which represent z as a linear combination of x, x1 to xk? Then it's called linear independent. So otherwise, we say z is linear It's very, very simple and straightforward definition, but very useful. And further, we can consider all the set of all the vectors which are linear dependent on x. We call this set of vectors as span of x. So the span of x is defined as the set of all vectors which can be represented as a linear combination of the vectors in x. This is called a span of x. And of course, if some vector z is linear independent to x, then it does not belong to span x. So this is the concept of linear independence. And further, we can talk about whether a set of vectors are linear independent. See, we can consider whether this set of x, this set x is linear dependent or linear independent. So if any vector in x, this big X, are linear independent to the remaining vectors, then we call x is linear independent. Okay. So x is linear independent if any vector in x cannot be expressed as linear combination of the other vectors. This x is called linear independent. Means that it cannot be compressed. Linear dependent means that there is some redundancy. I mean, actually, for example, x1 can be represented by x2, x3 to xk. Then actually, it's not necessary to keep x1. I can just kick it out. That's fine. But if any element cannot be expressed by other elements, other vectors, then it's not redundant anymore. It is most compact. So here I give you an example. I won't go through this example in the course material. You can take a look. I give you a more interesting example. So suppose in a three-dimensional space, right? Let me define my x to have three vectors: x1 is 1, 0, 0, x2 is 0, 1, 0, and x3 is 0, 0, 1. So first the question is whether x is linear dependent or linear independent, the whole x. Why?
Because any vector cannot be represented by the any other term.
Yeah. So you can say for x1, the first element is 1, right? But the first element for the remaining vectors are always 0, meaning that no matter how you choose the coefficients, their combination, their linear combination of their corresponding first element is always 0. So it cannot represent x1. Similarly, you can say for x2, the second element is 1, but the second elements for the remaining vectors are always 0. So it cannot be expressed as a linear combination of other vectors. Similar things apply to x3. So obviously x is a linear independent. The second, for arbitrary three-dimensional vector u, is it linear dependent on x or linear independent? So let me write down its coefficient, its elements is u1, u2, u3. So this is arbitrary. So the question would be whether u is linear dependent on x or linear independent on x.
Dependent.
Why?
Because u will be equal to u1 times x1 plus u2 times x2 plus u3 times x3.
Yeah, excellent, right? So you can find that it is easy to express as u1 times x1 plus u2 times x2 plus u3 x3. You can verify this. This is very straightforward.
That's because X is the basis, right?
Yeah,
So,
yeah. That's something I want to ask.
Okay.
So now we can say arbitrary three-dimensional vector can be represented by linear combination of x1, x2, x3. So then the question would be, what's the span of x? Span of x is what? What is span of x?
Three-dimensional vector within R. Right?
Yeah. Because the arbitrary three-dimensional vectors can be represented by the linear combination, meaning that this span of x consists of the whole three-dimensional space. So why is this set of vectors so powerful? Why?
Because it can represent any vector in three dimensions.
Yeah, closer. Can you express it more explicitly?
I guess it's any vector will always be linear dependent on that one.
Yeah, of course. But it actually corresponds to what? In a geometry point of view. But let us try to write down the three-dimensional space, right? So this is three axes. So how can we represent three axes? Yeah, they correspond to three vectors. So you can write x as a 0, 0, 1, y is a 0, 1, 0, and z is a 1, 0, 0. Okay. So it actually represents three axes. So actually any point in this three-dimensional space is represented by the coefficients on the three axes. So now I can say these three axes actually can represent any point in this whole dimensional space. So we can see why it is so expressive, so powerful. Okay, we stop here. And later this class will release the second homework. And to ensure you are happy fall break, so you're required to finish the homework on the Monday of the week preceding to the fall break, so that you won't leave any homework deadline during the fall break. So hurry up.